So at the beginning of this chapter, I promised that we would be able to take information about individual molecules and be able to find macroscopic properties. But so far, we're talking about these, copies, these imaginary copies of systems and this ensemble. How does this actually figure into calculating something? Once we have probabilities, we can start thinking about what's going to happen for our, what's the average result for our system. And the first thing we're going to look at is energy. So this symbol here, this just means average. And what is the average energy for our system? Well, the average energy for our system, if we know the probabilities, is actually fairly straightforward. We take a sum over all the possible energy values and take the probability of a system being in that energy times the energy. This is a different way of writing an average. Say you roll a dice and you want to know what's the average value of the dice roll. Well, you could take the probability of a specific value. So for a dice, that would be 1 over 6 for any given face of the dice. And you would multiply it by the value, and that would tell you the average. So if you take 1 over 6 times 1 and add that to 1 over 6 times 2 plus 1 over 6 times 3 and go up to 6, that would tell you the average value of the dice. You could, of course, add up all 6 values and divide by the total number. That would also give you the average, right? This is just a slightly different way of thinking about it. We can go ahead and substitute what we know for P sub j is e to the minus beta E sub j over our partition function Q times E sub j. Still have the sum. Let me make some space for that. Sorry about the ugly summation symbol there. But this tells us how we can find the average energy of our system. Now this equation is not super practical by itself, but let's express this just in terms of Q. And let me show you, this is not exactly a proof, but it's sort of showing there is a different way we can write this. Let's look at the partial derivative of the natural log of the partition function with respect to beta, holding n and v constant. Now you might wonder why do this. And what we'll see is that this relates to this average energy equation that we just wrote. So we can say, okay, this is also equal to 1 over q times dq d beta, so we can get rid of the natural log. These are equal to each other by use of the product rule, or I should say the chain rule. And then we can write the definition of our partition function. So the partial derivative of this sum with respect to beta. So we're going to have, for our derivative is going to be a sum. So we can think of the derivative of each term of the sum. We'll get negative beta times e to the minus beta e sub j. That's just by the definition of the property of the derivative of an exponential. So we'll get this is equal to 1 over q. And we have all these terms, each derivative. We'll get minus e sub j. Oh, because minus e sub j, sorry, not beta. We'll get negative e sub j times e to the minus beta e sub j. The reason for that being is that we're taking the derivative with respect to beta. Okay, and that is equal to, and then we can bring q inside the sum if we want to. That is equal to negative sum over j e to the minus beta e sub j over q times e sub j. And what you hopefully will notice here is that this equation and this equation look almost the same, the difference being this negative sign. And so we have shown that there's a way we can write the average energy. The average energy of our ensemble is equal to negative of this derivative, d log q d beta. What that means is if we can find an expression for q, right, if we know q, we can find the average energy of our system. So here's a concrete way that if we understand the microscopic properties of the system to be able to calculate Q, then we can find the average energy of a macroscopic system with an arbitrary number of particles. If we want to write this in terms of beta, we sometimes want to use temperature directly. We can use the chain rule to get this. The derivation is in my notes. I'm just going to write the final answer here. What you end up with is negative kBt squared d log q dt, keeping n and v constant. Right, so this is if you want to use temperature instead of beta as your variable of interest. In the next video, we'll look at an example of doing this, of calculating average energy for a real partition function, which we will look at how to get this in the next chapter, for a monatomic ideal gas.